For this lecture, we're going to look at 2.7. It is the section dealing with everything with absolute values in terms of functions. So first thing we're going to talk about is absolute value being a function. So we're going to write it as f of x is equal to the absolute value of x. This is y is equal to the absolute value of x. And this is one of our common parent functions. This is a parent function. That means that any absolute value function, no matter how it's being manipulated, when graphed, can be manipulated through the graph of the basic function absolute value of x. So before we get any further into the section, we want to graph what the absolute value of x looks like. So we're going to create a table of values. If we don't know what a graph looks like, the step is you should always create a table. And our x values are going to range from -2 to +2. And if we want to graph them, we're just going to plug these points into the function. So it'd be the absolute value of -2, which is 2. The absolute value of -1, which is 1. The absolute value of 0 is 0. The absolute value of +1 is 1. And the absolute value of 2 is 2. So now that we have 5 distinct points on this graph, we can come over here and sketch it. We're going from -2 to 2 on the x-axis, and you look at the y values. The largest y value is +2, the smallest is 0. And we're going to plot this as a series of ordered pairs. So we've got the ordered pair -2, 2, -1, 2, I'm sorry, -1, 1, 0, 0, the origin, 1, 1, and 2, 2. And if we connect these, this is a direct relationship where we have the parent function is actually a V-shaped function. So this is a V-shaped function. If you remember from 2.6, the quadratic f of x equals x squared is a U-shaped function known as a parabola. This is a V-shaped function. And then there's a few common things to make note of. Just like with a parabola, there's an imaginary line that runs down the middle of the graph. This red dotted line that I have drawn is called the Axis of Symmetry. This is the Axis of Symmetry. And if you look at this, this is the line where if you were to reflect this function or rotate it about that line 180 degrees, the left side would be mapped onto the right side and vice versa. In this case, the axis of symmetry, well, it's a vertical line, so it's an x equals equation, and it's x equals whatever the value of your vertex is, and the x value here is 0, so it's x equals 0. And then once again, same as with the parabola, this bend in the graph is called the vertex, and if the function is not manipulated, the vertex is at 0, 0. Now, with this being a parent function, that means that we have transformation rules, just like we did in section 2.6. We had transformation rules, and those same rules, the transformation rules, those same rules, I need to zoom the camera down, apply for this function just as they did for the linear function and the quadratic function. You do not need to write these rules down. You already have them in your notes, but I'm going to rewrite them just for reference. So just quickly going over the transformation rules, it says given that k is a positive number and a is a positive number, the following rules apply. F of x plus k means to translate up k. F of x minus k means to translate down k. The function of x plus k is to translate left k. F of x minus k means to translate the function right k units. F of negative x means it's a reflection about the y-axis, and the negation of f of x is an x-axis reflection because we're negating the y values. And then 2 constant multiple rules. If you have a times f of x and a is greater than 1, that's a vertical stretch. Whereas if a is a fraction between 0 and 1 or a decimal between 0 and 1, it represents a vertical compression. So with those rules in place, I want to do a few examples of these rules being put into place. Let's say our first example is graph f of x equals the absolute value of x plus 2. You should not need to actually draw or make a table of values to draw this graph. You should just understand transformations, and you should know that the original absolute value equation, the parent function, has an axis of symmetry of the y-axis, or the x equals 0 equation, and a vertex at the origin. So this is our graph of absolute value of x. And then you should just know that when you add 2 to the entire function, that's just moving the graph up 2. So this is a translation of absolute value of x up 2 units. So instead of being at the origin, this point is going to be at 0, 2, and then every point to the left and right, everything to the left and right is going to follow suit in its behavior. So therefore, this would be the graph of the absolute value of x plus 2. Now let's say we were to have g of x is equal to the absolute value of x minus 4. You should look at this and notice that, okay, the parent function is absolute value of x. So we have the parent function, absolute value of x. This is the absolute value of x minus 4. So we have the x inside of the absolute value being manipulated. So that's still a translation rule. And when it's a subtraction, it's a translation to the right 4 units. So it's going to be the exact same picture, but we're going to shift everything to the right 4 units. So instead of being at the origin, we're now going to be at 4, 0, and then all of the other points will follow suit. Now when you do that, looking up here, the vertex was at 0, 2, but the axis of symmetry, we'll call that AOS, is still at x equals 0. When we move this one, x minus 4, we translate it right 4 units. The vertex is at 4, 0. Our axis of symmetry has also moved. Our axis of symmetry is now a vertical line, so it's x equals, and it's x equals, well, the x-intercept is 4. It's always x equals the numerical value of our x-coordinate of our vertex, so x equals 4. And that should make sense because if you were to imagine reflecting this V-shaped curve, V-shaped line over x equals 4, which is a vertical line, the picture of x minus 4 remains the same. Now, one thing we covered in 2.6 is when we add amplitude into it. So let's say we have k of x is equal to 2 absolute value of x. So in all of the other functions, the amplitude has been 1. So the amplitude is now 2. And maybe make note, 2 is greater than 1. That means this is a vertical stretch by 2. So it's a vertical stretch by 2. It's going to become twice as tall. So for this, the origin is going to stay at 0, 0. The parent function, absolute value of x, passes through the point 1, 1 and negative 1, 1. And this just says we're going to make our y values, absolute value of x is our y values, we're going to multiply by 2. So we can kind of think of slope or amplitude as slope. Amplitude is 2 over 1. Now, if you remember what I made a comment when we were doing the quadratic function. This only tells you how to get from the vertex to the very next point. So 2 over 1 means we would go up 2, right 1. So rather than going up 1 over 1, which is the parent function, absolute value of x, we're now going to go up 2, right 1. And then we're going to do the exact same mirror image. It's going to be up 2, left 1. So in doing so, we've got this new function, which is 2 absolute value of x. And if you look at it, it is twice as steep as the parent function, absolute value of x. All right, now let's take a look at one. Let's call it m of x, where the amplitude is less than 1. Okay, so if we notice here, amplitude is 1/3. That's less than 1, which means this is going to be a vertical compression. So if we go to sketch this graph, we go back to the parent function every time. The parent function, absolute value of x, looks like this. It passes through the origin and the points 1, 1, and negative 1, 1. This says our amplitude is 1/3. So instead of going up 1, right 1, we're going to go up 1, right 3. So looking at this picture, we're going to go up 1, right 3. And then we're also going to do the mirror image of that. Up 1, left 3. So this is exactly 1/3 of the height of absolute value of x. This is being compressed by a factor of 1/3. All right, and then lastly, before we move into any further in depth, for the fifth one, let's look at the function f of x equals the negative of the absolute value of x. Now, this is a negation of the y values. We're negating the entire parent function. So, since this is the negation of the entire parent function, this is a reflection about the x-axis. So, this is an x-axis reflection. And if you think about this, if we were to go to draw this, here's our parent function, absolute value of x. And then we're going to reflect this across the x-axis because the negation of the absolute values is the definition of transformation, the transformation where we reflect it about the x-axis. So when we negate the absolute value of x, that's just going to take this curve and flip it, which now makes this new picture look like this. The purple is the graph of the negative of absolute value of x. And if you think about this, note, negative absolute value of x. The amplitude is the number in front of the absolute value. There's a negative 1 there, which can be written as negative 1 over 1. And if you remember when we did slope, negative 1 means we wouldn't go up 1, we would go down 1, right 1. So rather than going up 1, right 1, we're now going to go down 1, right 1. So one thing that can be said about the amplitude being negative 1 is we can also think of this negative as a direction of opening. So when it's just the absolute value of x, just the parent function, it opens up. But when you negate it, it causes the absolute value function to then open down. So with that said, we can then do combinations of transformations. The f of x equals negative 2 absolute value of x. So if you look, we have it's being negated, which means there's an x-axis reflection, and it's being multiplied by 2. It being multiplied by 2 represents a vertical stretch by 2. So if we were to graph this, we have the original function, which is starts at the origin, up 1, right 1, up 1, right 1. Then taking care of the amplitude for this, the negative causes it to open down. The amplitude being negative causes the graph to open down. And the 2 tells you how steep it is. So now we're going to go open down, and we're going to go down at a rate of 2 over 1. Down 2 over 1. So we're applying the same concept with amplitude. negative 2 over 1. If you think about that, it's down 2, right 1. And then we do the mirror image of that. The negation tells you to open down. The 2 tells you how much to open down for that initial point, down 2 over 1, and vice versa. Now, if we were to put a series of these together, let's say we have this. 1/3 x plus 3 minus 4. So the 1/3 is the amplitude. That means we have a vertical compression because it is less than 1. So vertical compression by 1/3. We have a, you guys can't see anything that I've done in the last 30 seconds. Number 7 is g of x equals 1/3, absolute value of x plus 3 minus 4. The amplitude being 1/3 tells us there's a vertical compression by 1/3 because it's less than 1. The plus 3 means we're going to translate. And then remember, when you add 3 inside of the function, that's doing the opposite of what you would think. So that's a translate left 3. Minus 4 means we're going to translate left 3 down 4. And there's a series of ways you can do this. You can either do them all at once or you can do it in successive steps. I prefer to do it all at once. We're going to take the original function, which looks like this. And we're going to move it left 3. So we're going to take this origin point, move it left 3. So we have 1, 2, 3. So we're now at negative 3, and we're going to go down 4. 1, 2, 3, 4. So we're going to need to, then it has an amplitude of 1/3. So we moved it left 3, down 4. That's taking care of the vertical and horizontal translation. Now we're going to take care of the 1/3. Well, remember, 1/3 is positive, means it should open up. And then the amplitude tells you how to get to the next point. So it's up 1, right 3. So from the new vertex, we're going to go up 1, which puts us here, and right 3. And then from the vertex, we're going to go up 1, left 3. So when we've done that, now our vertex is at negative 3, negative 4. And we have a new axis of symmetry. The axis of symmetry is x equals, because it's a vertical line, so it's an x equals equation. And it's always x equal the x value of the vertex, which in this case is negative 3. That brings us to the next part of the notes where we talk about how to identify the vertex and axis of symmetry without actually drawing the graph. If you look here, this was 3. It turned into negative 3. This was negative 4. It stayed negative 4. So we're always going to change what's inside of here, keep what's on the outside. This brings us to the last part of the notes. Given f of x equals a, absolute value of x minus h plus k. If you look here, this is just a absolute value function that has been some kind of horizontal translation, some kind of vertical translation, and some effect on the amplitude. So this is just a transformation of the absolute value parent function. So given f of x equals this, the vertex of the function, and if you remember what I just said in the last example, we're going to change this and keep that. So if we change negative h, we get h, and if we keep k, it becomes k. So the vertex of the function is hk with an axis of symmetry of x equals, and remember, the axis of symmetry is always the line that runs down the middle. The line that runs down the middle always corresponds to the x value of the vertex. So it's going to be a vertical line that has the same x value as the vertex. Now with that said, without graphing, identify the vertex and axis of symmetry for each. All right, so this is last part of the notes. Let's say we do number 1. Let's say we have y is equal to 2 absolute value of x minus 3 plus 6. This is an absolute value function. It's of the form a absolute value of x minus h plus k. There's transformations going on. We could graph this. We're going to move it to the right 3. We're going to move it up 6. And we're going to stretch it by a factor of 2. Rather than doing that, we can get the answer without graphing, we can tell what the vertex is. Okay, let me use a different color. The vertex is, you change this number, negative 3. You keep this number, which is 6. And we can identify the axis of symmetry. Remember, the axis of symmetry is that vertical line that runs down the middle of the graph. It always has an equation of x equals whatever number we have for our x coordinate of our vertex. Now, if we go to a graphing calculator, or you can graph it by hand, but if you're not sure, you can go to a graphing calculator such as the one I have on the board. This is a Desmos.com that I mentioned a few days ago in class. If I were to type in y equals the absolute value of x minus 3 plus 6, and then multiply all that by 2, I have to zoom out to see it. But if you look here, I have a absolute value function where the vertex is at 3, 6, which is what we have in our notes. And if I type in x equals 3, that graphs the axis of symmetry, which is a vertical line that passes through the x-axis at the point 3, 0, which is also what I have in our notes. So, let's do a couple more examples. Let's say we have y equals negative x plus 4. Well, the question might arise, well, wait a minute, we don't have anything over here. If there's nothing over there, we can add something. We can still put a plus 0. So then it still makes getting the vertex possible. The vertex is you change this, keep that. So the vertex is at negative 4, 0. And the axis of symmetry is the vertical line x equals and whatever the x value is of our vertex. So x equals negative 4. If we go to a graphing calculator to check this out, let's change this to negative absolute value x plus 4. And I don't have anything going on here. If you notice when I graph that, it gives us a absolute value function that's opening. Well, the amplitude was negative, so it should be opening down. Vertex is at negative 4, 0. And the axis of symmetry was x equals negative 4. So we type that in, we get a vertical line that runs right through the middle of the graph. All right, and then the last example for this section is going to be, what if we had y equals 2 absolute value of x minus 1. Same theory applies. It is of the form, since there's nothing being added or subtracted in the parentheses, we'll put a plus 0 right here. So this is the same as 2 absolute value of x plus 0 minus 1, which then makes the vertex easy to identify. The vertex is you change this. Well, the negation of 0 is still 0. Keep negative 1. And the axis of symmetry is the equation x equals, and then it's 0, because that corresponds to the x value of our vertex. And then, so, if we look at this, we're going to type this in, y equals 2, absolute value of x, minus 1. We get a absolute value function that's been moved down 1. We should, because that's a minus 1. Opening up because the amplitude's positive 2. And it's opening up by a factor of 2. So if we check this, how do we get from here, the vertex, to the next point? The next point is at 1, 1. So it goes up 2, right 1. And then the axis of symmetry is at x equals 0. And we get a vertical line that runs down the middle of the graph. So that means we've done our problem correctly. That finishes up for this section, guys. This is section 2.7, absolute value functions. Outside of class, if you're still having trouble with this, you can go to YouTube, absolute value functions, type this in, 2.7, absolute value functions, and then add my name at the end. Aaron McCann. That's the best way to find this video. If you type this in along with my name, it should be one of the first 2 or 3 that pop up, which will give you access to this video outside of class. Also, same as always, if you need to email me with any questions, my email is aaron.mccann, all lowercase, at ovsd.us. The assignment for this is going to be 2.7 practice. The entire worksheet, front and back. 2.7 practice, front and back. But I want you to omit the following problems. So 2.7 worksheet. But I want you to omit. That means do not include. You can mark these out. Number 12, 17, 19 through 21, and 23. These problems have something a little slightly different than how I've showed it in the video. I'll explain it when I get back, but for right now, you have enough information to do the rest of the worksheet, and then we'll discuss this when I get back on Friday. Have a good rest of the day.